For over 4,500 years, they have stood massive, silent, and unyielding. Rising from the sands of Giza like ancient sentinels, the pyramids have defied storms, time, and even our understanding of engineering. How were they built? By whom? And perhaps most puzzling of all, why? Theories have ranged from ingenious ramps to alien spacecraft, from water-powered lifts to mystical energies. But beneath the wild speculation lies a deeper story, one of human ambition, divine symbolism, and relentless innovation. This is the epic tale of how the pyramids might have been constructed, and why the mystery still refuses to die. A civilization of stone, few structures on Earth inspire such awe as the Egyptian pyramids. Constructed during the Old Kingdom, centuries before the rise of Athens or the Roman Empire, these monuments emerged in a world where bronze was still cutting-edge technology. And yet the builders achieved feats that challenge modern engineers. The Great Pyramid of Khufu alone consists of over 2.3 million stone blocks, some weighing more than 70 tons, aligned with celestial precision to the cardinal points. What makes the mystery truly gripping is the lack of contemporary records describing the methods of construction. While temple inscriptions and tomb paintings survive, none explicitly outline how to build a pyramid. This silence has allowed centuries of theories to flourish. Ancient historians like Herodotus imagined elaborate machines. Medieval travelers invented myths of magic. Modern engineers propose ramps, pulleys, and hydraulics. The result is a puzzle layered with history, speculation, and cultural imagination. But before we explore the dizzying array of theories, we must first travel back to the dawn of pyramid building. Because to understand how these monuments were constructed, we need to understand why they were built in the first place, and how a civilization mastered stone architecture on a scale never seen before. The birth of the Pyramid Age. From mastabas to monuments. Long before the world marveled at the towering perfection of the Great Pyramid, Egypt's journey toward monumental architecture began humbly in the form of mastabas. These were low, rectangular mud-brick tombs with sloping sides and flat roofs, built above underground burial chambers. They lined the cemeteries of early elites, especially during Egypt's first and second dynasties. Each mastaba was not just a tomb. It was a statement of status, designed to endure the desert winds and guard the deceased's journey into the afterlife. As Egypt's political structure centralized and pharaohs consolidated power, these mastabas grew larger, more elaborate, and increasingly symbolic of a ruler's divine authority. Then came Imhotep, the genius architect and vizier of Pharaoh Djoser, who would ignite a revolution in Egyptian architecture. Around 2630 BCE, at Saqqara, Imhotep dared to stack mastabas atop one another, layer by layer, creating something no one had ever seen, a six-tiered step pyramid rising over 60 meters high. It was both architectural brilliance and theological innovation. This was no mere tomb. It was a stairway to the heavens, a structure that embodied Djoser's divine role as a bridge between the human and the celestial. For the first time, stone was used on a massive scale, replacing perishable mud brick. Egypt had entered the age of stone architecture. The step pyramid also demonstrated something crucial: the state's ability to mobilize and coordinate massive labor forces. Thousands of workers, artisans, quarrymen, and planners collaborated under a centralized system that combined religious devotion, political power, and practical ingenuity. Imhotep's project was not just about engineering. It was about the emergence of a new kind of state-sponsored monumentality, where a pharaoh's ambitions were matched by national organization and technical skill. This step pyramid became the prototype for all future pyramids. It revealed that Egyptians could build upward, that stone could be shaped and placed with precision, and that monumental projects could be realized through planning and manpower. It was a turning point. No longer were tombs hidden beneath sand or modest structures on the surface. They could dominate the landscape. This set the stage for the smooth-sided pyramids that would soon rise on the horizon, monuments that would push the limits of human capability and reshape the world's architectural imagination. Finally, the step pyramid marked a shift in religious expression. It wasn't merely a tomb, it was a theological machine, built to ensure Djoser's transformation into an eternal divine being. The physical act of ascending the pyramid mirrored his spiritual ascent to join the gods. This powerful fusion of architecture, religion, and politics would define every pyramid that followed. The birth of the Pyramid Age was not a single moment, but a confluence of innovation, ambition, and belief. The reign of pharaohs. Why pyramids were built. To understand how the pyramids were constructed, we must first ask why they were built at all. In ancient Egypt, the pharaoh was not merely a king, he was believed to be a living god, the vital bridge between the mortal world and the divine realm. His reign extended beyond the grave. In death, he was expected to ascend to the heavens and join the gods, particularly Ra, the sun god. The pyramid was the vessel that facilitated this divine transformation. It wasn't just a tomb, it was a meticulously designed resurrection machine, a spiritual launchpad crafted from limestone and belief. Each pharaoh sought to leave a legacy that proclaimed his divine power for eternity. Earlier rulers had built mastabas, rectangular tombs with flat roofs, but these structures didn't match the grandeur of their god-king status. When Pharaoh Djoser commissioned Imhotep to design the step pyramid at Saqqara, the concept of a monumental tomb took a revolutionary leap. This structure signaled that pyramids were more than burial chambers. They were instruments of propaganda, cosmology, and immortality. The pyramid's colossal scale served a dual purpose. It asserted the pharaoh's divine authority over Egypt's people and cemented his memory in stone long after his death. To the common laborers who toiled under the blazing sun, the pyramid was a holy project that honored their ruler and secured their own place in the cosmic order. Contributing labor to the pharaoh's tomb was considered a sacred duty, one that connected ordinary Egyptians to the divine narrative. It's important to recognize that these projects were not spontaneous acts of ego. They were calculated, spiritual, and deeply political undertakings. Each block laid was a testament to a civilization that believed their rulers controlled both the Nile and the afterlife. The motivations behind pyramid building reveal a culture where religion and state were indistinguishable, and monumental architecture was the language through which rulers communicated with eternity. Ancient Egyptian tools and workforce, known facts. Before we get swept up in wild theories, it's worth grounding ourselves in what we do know. Archaeological evidence provides a surprisingly detailed picture of the tools, techniques, and workforce that the Egyptians employed. Contrary to popular myth, the pyramids weren't built by slaves in chains. They were constructed by a massive organized labor force composed of skilled workers, seasonal farmers, and artisans. Excavations at Giza have uncovered entire workers' villages complete with bakeries, breweries, medical facilities, and dormitories, evidence of a well-fed, well-managed community. Their tools were surprisingly simple, but highly effective. Copper chisels, dolerite pounding stones, wooden sledges, and ropes made of papyrus and palm fiber were the backbone of construction. These tools may sound primitive to modern ears, but they were perfectly suited to the task. Dolerite, a particularly hard stone, was used to pound and shape limestone blocks with remarkable precision. Sledges hauled the massive stones across prepared pathways, often lubricated with water to reduce friction. The workforce itself was divided into well-structured teams. Archaeologists have identified crews with names like the Drunkards of Menkaure and the Friends of Densa, Khufu, suggesting both camaraderie and a sense of pride in their labor. Workers rotated seasonally, often during the annual Nile flood, when farming wasn't possible, which provided Egypt with a steady and immense labor force. This organization speaks to a civilization capable of planning on a scale that even modern governments struggle to match. The sophistication of this workforce and their methods dispels the notion that pyramid construction relied on mysterious lost technologies. It demonstrates that a well-coordinated society, armed with determination, religious motivation, and clever engineering, could achieve the seemingly impossible, all without cranes, lasers, or alien intervention. Geology of the Giza Plateau, stone, sand, and stability. The Giza Plateau wasn't chosen by accident. It provided the ideal geological foundation for the construction of colossal stone monuments. Underneath the sands lies a stable layer of limestone bedrock, hard, solid, and capable of supporting the immense weight of the pyramids for millennia, without shifting or collapsing. This geological stability was crucial. Without it, even the most ingenious building methods would have failed. The site's proximity to quarries was another decisive factor. Much of the limestone used in pyramid construction was quarried directly on site, reducing transportation challenges significantly. For the outer casing stones, finer limestone was brought from Tura across the Nile, and granite blocks used in the inner chambers were transported from Aswan hundreds of kilometers to the south. This combination of local and imported materials created both structural strength and aesthetic brilliance. Environmental factors also shaped the construction strategy. The plateau's elevation kept it safe from Nile flooding, while its firm rock allowed for precise leveling, something the Egyptians mastered to an astonishing degree. Some measurements show that the base of the Great Pyramid is level within a few millimeters, a feat that modern engineers still marvel at. The builders used water-filled trenches and meticulous surveying techniques to achieve this near-perfect foundation. Understanding the geology reminds us that pyramid construction wasn't merely about stacking stones, it was about harnessing the land itself. The Egyptians read their environment with scientific precision, selecting a site that would transform natural stability into architectural eternity. Religious and cosmic symbolism in pyramid design. Beyond their physical presence, the pyramids were saturated with religious and astronomical meaning. Their very shape, a triangular form rising to a single point, symbolized the sun's rays beaming down to earth. Pharaohs believed that by being entombed within these structures, their souls could ascend along these rays and join Ra in the heavens. The pyramid was essentially a cosmic elevator, its geometry aligning human ambition with divine architecture. The orientation of the pyramids further underscores their symbolic role. The sides of the Great Pyramid align almost perfectly with the cardinal directions north, southeast, and west, a level of precision achieved without modern compasses. Many scholars believe the ancient Egyptians relied on the stars, particularly the circumpolar constellations that never set, to guide their alignments. To the Egyptians, these stars represented immortality, further linking the pyramid to eternal life. Reliefs, texts, and burial practices reveal that every chamber, passageway, and alignment carried spiritual significance. The internal shafts of the Great Pyramid, for example, were believed to align with specific stars like Sirius and Orion's belt, celestial markers of the afterlife. The pyramid's design was both a physical structure and a metaphysical map, guiding the pharaoh's soul on its journey to eternity. This cosmic symbolism reflects a worldview where religion, science, and architecture were inseparable. The pyramids weren't just monuments. They were the physical embodiment of Egyptian cosmology, anchoring divine principles in stone. Straight ramp theory, the classic Egyptological model, for over a century. The straight ramp theory has dominated mainstream explanations of pyramid construction. According to this model, massive linear ramps were built from mud brick, rubble, and limestone chippings, extending from the ground all the way to the pyramid's upper courses. As each layer of the pyramid rose, the ramp was lengthened and heightened, allowing workers to drag the immense stone blocks up its slope on sledges. It's simple in concept, a massive, gradually inclining highway that functioned as the artery through which the pyramid's building materials flowed. The appeal of this theory lies in its straightforwardness. It requires no exotic technologies or speculative inventions, just an enormous amount of material and labor. Egyptologists argue that the Nile floodplain's abundance of mud brick and rubble could have provided enough material to build and dismantle these ramps. Archaeological evidence of large ramps near other pyramid sites, sets at the Pyramid of Medum and the unfinished pyramid at Zoyat Ilarion, lends some weight to this model. However, the straight ramp theory faces serious practical problems. The length of the ramp required to maintain a workable incline of about 7 to 10 degrees would have been staggering, potentially more than a mile long for the Great Pyramid. Constructing, maintaining, and later dismantling such a colossal structure would have demanded more resources than the pyramid itself. Moreover, evidence of such massive ramps has not been found at Giza, which raises questions about the theory's feasibility at that specific site. Despite these criticisms, the straight ramp model remains the baseline against which other theories are measured. It represents the earliest academic attempt to explain pyramid building using known materials and methods, and its simplicity continues to make it a strong candidate for at least part of the construction process. Most modern theories build upon or modify this model rather than rejecting it entirely. Zigzag ramp theory, solving the length problem. To address the challenges posed by the immense length of straight ramps, some scholars have proposed zigzag or switchback ramp systems. Instead of stretching out in a single linear path, These ramps would zigzag up one face of the pyramid, reducing the amount of material needed and keeping the construction site more compact. Imagine a series of ascending switchbacks carved into the pyramid's facade or built alongside it, snaking back and forth as the structure rose. The main advantage of this approach is efficiency. A zigzag ramp would have required far less material than a mile-long straight ramp, making it easier to construct and dismantle as needed. Workers could move stone blocks upward along the shorter, steeper ramps, possibly using wooden sledges lubricated with water to reduce friction. Some reconstructions suggest that as the pyramid grew taller, older sections of the ramp could be dismantled and their materials recycled higher up the structure. One of the key arguments in favor of zigzag ramps is the lack of physical evidence for massive straight ramps at Giza. A zigzag system would have left a much smaller archaeological footprint, which could explain why no colossal linear ramps have been found. Additionally, this method might have allowed construction on multiple pyramid faces simultaneously, speeding up the process significantly. However, zigzag ramps present their own logistical challenges. Turning massive stone blocks at switchback corners would have required careful coordination, and the ramps would have had to be built with precise engineering to avoid collapse. Nevertheless, the theory offers a compelling alternative to the unwieldy straight ramp, blending practicality with architectural ingenuity. Internal spiral ramp theory, Jean-Pierre Houdin's proposal. Perhaps the most elegant modern theory is that proposed by French architect Jean-Pierre Houdin, who suggested that the Great Pyramid was constructed using an internal spiral ramp. According to Houdin, the Egyptians built the lower portion of the pyramid using a traditional straight ramp. But once they reached a certain height, they began hauling blocks up a spiraling corridor constructed inside the pyramid's outer casing. This ingenious system would have allowed construction to continue upward without requiring massive external ramps. Houdin's model was based on detailed 3D modeling and engineering analysis. He noted that if a ramp spiraled just inside the outer shell, workers could haul stones in a sheltered environment, protected from wind and sun. Openings at the pyramid's edges would have allowed the stones to pivot around corners. His theory gained traction after microgravimetry scans revealed anomalies in the pyramid's internal structure that could correspond to these hidden ramps. One of the strongest points in Houdin's favor is that his model neatly resolves the ramp material problem. An internal spiral would require far less material than external ramps. And because it would be dismantled as construction proceeded upward, there would be little to no archaeological trace left behind. This explains the mystery of the missing ramps while maintaining historical plausibility. While direct proof of the internal spiral ramp remains elusive, no physical corridor has yet been uncovered. Many engineers find Houdin's model both structurally sound and logistically efficient. It represents a brilliant marriage of modern technology and ancient ingenuity, making it one of the most widely discussed pyramid theories of the 21st century. Combined ramp systems, hybrid approaches. Many modern Egyptologists and engineers argue that the pyramids were not built using just one method, but rather a combination of several. The hybrid models suggest that different ramp systems were used at different stages of construction. For example, a short straight ramp might have been used for the lower courses, after which workers transitioned to zigzag or spiral ramps as the structure rose higher. This approach would maximize the strengths of each system while minimizing their drawbacks. Hybrid models are attractive because they align with how large construction projects typically evolve, adapting to circumstances as they change. Early stages of pyramid building required hauling the heaviest and largest blocks, such as the granite beams in the king's chamber, which would have been easiest to do with a broad straight ramp. As the pyramid climbed, smaller blocks and finishing stones could have been raised with more flexible ramp systems, scaffolding, or even lifting devices. Some hybrid theories even propose the use of temporary wooden towers or pulleys on upper levels, integrating mechanical aids alongside ramps. This layered strategy helps explain why no single ramp type fits all aspects of the pyramid's construction and why archaeological evidence seems scattered or incomplete. Each stage may have left behind different kinds of traces, some of which have eroded over millennia. While hybrid approaches can be more complex to visualize, they arguably reflect a more realistic scenario. Ancient Egyptians were pragmatic builders, not ideologues wedded to one method. Combining multiple techniques to adapt to evolving challenges fits both their ingenuity, and the practical demands of such a colossal project. Lever and pulley systems. Mechanical ingenuity of the ancients. The use of levers, pulleys, and simple machines has been a recurring theme in pyramid construction theories. Some Egyptologists believe that once the base levels were completed, the Egyptians relied increasingly on lever systems to lift stones upward. Workers could have used wooden beams pivoted on fulcrums to gradually raise blocks from one level to the next. By repeating this process in stages, stones could be lifted surprisingly high with minimal manpower. Pulleys, while not documented extensively in Egyptian records, might have appeared in primitive forms such as rope and groove systems that allowed workers to redirect forces efficiently. Even a basic fixed pulley can reduce friction and make lifting more manageable, especially when used in combination with ramps and scaffolding. Some theories suggest wooden A-frames mounted on the pyramid's tiers, enabling workers to hoist blocks upward using ropes. Manpower and simple mechanical advantage. The key strength of lever and pulley systems lies in their efficiency for vertical lifting. Unlike long ramps that consume enormous resources, levers and pulleys can be reused repeatedly with minimal material. If the Egyptians employed such methods in tandem with other systems, they could have conserved resources while maintaining steady progress on the upper sections of the pyramid. While no direct archaeological evidence of large-scale pulleys has been found at Giza, the mechanical principles were well within the Egyptians' technological grasp. They used levers extensively in other contexts, such as moving obelisks and heavy statues. It's entirely plausible that similar tools were adapted for pyramid construction, representing yet another layer of ingenious problem-solving in the ancient world. Rollers, sledges, and wet sand, practical transportation methods. Transporting massive stone blocks from quarries to the pyramid site was one of the greatest logistical challenges of the entire project. Archaeological evidence suggests the Egyptians relied primarily on wooden sledges to drag blocks across the desert. In 2014, a discovery at the tomb of Jutotip depicted workers hauling a colossal statue on a sled, while a man poured water over the sand in front. This wasn't ritual, it was physics. Wetting the sand reduces friction dramatically, allowing sledges to slide up to 50% more efficiently. This ingenious trick shows that the Egyptians understood how to manipulate their environment to move unimaginable weights without wheels. Some researchers propose the use of wooden rollers, but this idea faces difficulties. Egypt lacked an abundance of suitable hardwoods, and rollers tend to sink into sand under heavy weight. Sledges, by contrast, distribute weight more evenly. To move stones over longer distances, the Egyptians likely built temporary roadways, possibly covered with compacted gypsum or mud brick. Along these paths, teams of workers, sometimes numbering in the hundreds, would haul the blocks using ropes, chanting rhythmic work songs to synchronize their efforts. Transport wasn't just horizontal. At the pyramid site, the same sledges could be hauled up ramps, lubricated with water or animal fat. Some researchers suggest log rollers may have been used for lighter stones in controlled areas, especially during final casing placement. But for the bulk of construction, the sledge method remains the most plausible. It required no wheels, no advanced machinery, just clever use of natural materials and organized labor. This chapter highlights something essential about pyramid construction: brilliance through simplicity. Instead of imagining alien anti-gravity beams or futuristic cranes, the Egyptians relied on clever applications of basic principles. By combining sledges, lubrication, and prepared paths, they turned a daunting problem into a manageable one, a theme we'll see again in other construction stages. Scaffolding and external structures. While ramps get most of the attention, scaffolding and temporary external structures likely played a crucial supporting role. Wooden scaffolds could be erected around specific sections of the pyramid to provide access for workers installing casing stones, smoothing outer surfaces, or performing precision work at higher levels. These scaffolds were likely modular, allowing sections to be moved and reused as construction progressed upward. Wood was scarce in Egypt, but not entirely unavailable. Imports of cedar from Lebanon and acacia from local sources could have provided enough for lightweight scaffold structures, especially since these would be temporary and reused repeatedly. Wooden platforms might have wrapped around sections of the pyramid, much like modern construction scaffolds around skyscrapers. These would allow teams to work simultaneously on multiple levels, fitting, finishing, and hauling smaller blocks, without interfering with the main ramp systems. In addition to scaffolding, temporary external stairways or inclined paths could have been built along pyramid edges, particularly during the final stages when the external casing was being placed. These allowed precision placement of the fine-tura limestone blocks that gave the pyramids their gleaming white finish. Evidence of similar stepped scaffolding exists in tomb scenes, where builders are shown working on large stone structures using ladders and raised platforms. This system of scaffolds and temporary frameworks likely complemented the ramps rather than replaced them. Where ramps handled mass transport, scaffolding handled fine work and vertical access. It's a reminder that pyramid construction wasn't one single method, but an evolving choreography of techniques addressing a different challenge as the monument rose skyward. Temporary piers and causeways. Another often overlooked aspect of pyramid logistics is the network of temporary piers and causeways built to connect quarries, the Nile River, and the construction site. Egyptologists have found evidence that the ancient builders dug canals and harbor basins close to the Giza plateau, allowing boats to deliver limestone blocks almost to the foot of the pyramid. A recently discovered harbor complex at Wadi al-Jurf contained papyri, describing how stone was ferried along the Nile, a vivid testament to Egypt's logistical prowess. Once offloaded, stones were likely moved along temporary stone or mud brick causeways, which functioned like elevated highways across uneven terrain. These causeways would have been straight and gently sloped, facilitating smooth transport by sledge teams. They may have been dismantled after construction, which explains why their remnants are scarce. However, the Great Pyramid Causeway, which connected the pyramid to the Valley Temple, still stands as evidence of how important these transport arteries were. Temporary piers built into the Nile's edge would have served as docking points during the inundation season, allowing heavy stones to be delivered by barge when the river was at its highest. This seasonal rhythm of transport and construction synchronized Egypt's natural cycles with its building ambitions. By leveraging the Nile's annual flood, the Egyptians avoided the need to drag stones over land for miles. This infrastructure was as important as the ramps themselves. Without these piers and causeways, the logistics of transporting millions of stones would have been far slower and more chaotic. It shows that pyramid building was not just an act of brute labor, it was urban-scale engineering, involving waterways, roads, and temporary installations that turned Giza into a bustling seasonal construction hub. Stone cutting and shaping techniques. Before any stone could be hauled or lifted, it had to be cut and shaped with precision. The Egyptians worked with three main materials: soft limestone, harder limestone, and granite. For limestone, they used copper chisels, wooden mallets, and dolerite pounding stones. Quarrymen would carve trenches around blocks, insert wooden wedges, and soak them with water, causing the wood to expand and split the stone cleanly. The result was massive rectangular blocks ready for transport. For harder stones like granite used in the king's chamber and internal passages, the Egyptians relied on dolerite pounding balls, hard, round stones used to pound the surface until it cracked. Archaeological evidence at the Aswan quarries shows thousands of dolerite pounders scattered around massive, unfinished granite blocks. Once rough-shaped, finer chiseling and polishing created precise surfaces, some of which fit together so tightly that a modern razor blade can barely slip between them. Shaping was often done on-site at the quarry to reduce weight during transport. Blocks were then transported to the pyramid where final trimming and fitting occurred. Some casing stones display extremely fine finishes, likely achieved using abrasives such as sand to smooth surfaces to a brilliant polish. Despite their simple tools, Egyptian masons achieved levels of precision that still astonish modern engineers. This chapter underscores that pyramid construction wasn't just about moving blocks, it was about masterful stone craftsmanship. Their techniques were time-consuming but methodical, relying on patience, skill, and generations of accumulated knowledge. No alien lasers required just thousands of hands and sharp eyes, manpower, logistics, and seasonal labor force. Finally, none of these techniques would have mattered without the human workforce to carry them out. For centuries, popular myths imagined the pyramids were built by slaves, but modern archaeology paints a very different picture. Excavations at Giza have uncovered workers' villages complete with bakeries, breweries, and medical facilities, adjusting a well-fed, organized, and skilled labor force. These workers were likely seasonal laborers, drafted during the Nile's inundation when farming fields were submerged, giving farmers a temporary occupation. This system created a rotating labor force of tens of thousands, divided into teams and sub-teams, each with specific tasks. Graffiti found on blocks and walls showed that these teams had names like the Drunkards of Menkar or the Friends of Khufu, hinting at camaraderie and pride in their work. This wasn't forced labor on a massive scale, it was a national project that likely combined paid workers, conscripts, and specialists. Logistics were equally complex. Feeding, housing, and organizing such a workforce required centralized planning. Archaeological evidence shows massive bakeries capable of producing thousands of loaves per day, breweries for beer rations, and hospitals for treating injuries. Overseers coordinated the flow of stones, workers, and tools, turning the pyramid site into a temporary city, humming with activity. Understanding the human element strips away sensationalism and replaces it with awe for real people, whose sweat, skill, and determination raised these immortal monuments. They weren't nameless slaves. They were citizens participating in the greatest building project of their civilization. Lost high-technology hypothesis. For centuries, travelers have stood before the Great Pyramid and whispered the same question. Could the ancient Egyptians really have done this with copper tools and ropes? The lost high-technology hypothesis proposes that they didn't, that some forgotten civilization, predating dynastic Egypt, possessed advanced engineering knowledge that was later lost to time. This idea doesn't rely on aliens, but rather on the possibility that humanity's technological timeline may have deep, unexplored layers. Proponents point to the extraordinary precision of the stone blocks, the near-perfect alignment of the pyramid with the cardinal points, and the mathematical sophistication embedded in its dimensions. To them, the scale of the project simply doesn't match the conventional picture of a Bronze Age society. Supporters of this theory often highlight curious anomalies. Core drilling traces found on some granite blocks appear to show spiral tool marks that seem too regular for hand tools. In places like the Serapeum of Saqqara, massive granite sarcophagi, weighing over 70 tons, were carved with remarkable smoothness and right angles so perfect they rival modern machining. How, they ask, could such feats have been achieved with simple chisels and pounding stones? The mainstream explanation is that patience, skilled labor, and ingenious techniques can produce incredible results, but alternative theorists suspect some lost form of technology. Perhaps mechanical saws, advanced abrasives, or lifting devices was at play. An intriguing part of this theory involves the possibility of an earlier mother civilization, perhaps wiped out by a cataclysm, such as the end of the Younger Dryas period around 10,800 BCE, a time of abrupt climate upheaval. Could remnants of their knowledge have trickled down to the builders of Giza? Graham Hancock, for example, suggests that the pyramids are a legacy, not a beginning evidence that ancient humans had reached high levels of sophistication before history officially began. While mainstream Egyptology sees no direct evidence of such a civilization, this hypothesis thrives on gaps and mysteries that remain unresolved. Critics argue that the precision often cited is exaggerated or misunderstood. What may look perfect to the naked eye can reveal irregularities under modern measurement. Furthermore, the notion of lost technology can sometimes underestimate the ingenuity of ancient workers who had water shaft and hydraulic lift theory. One of the more ingenious alternative ideas involves water, not ramps. The water shaft theory suggests that the Egyptians might have used a series of internal canals and hydraulic locks to float the massive blocks upward. Much like ships passing through a system of locks in a modern canal, this theory gained traction when researcher Robert Carson proposed that the Nile's high floods were channeled through a system of dikes and basins, turning parts of the Giza plateau into temporary artificial harbors. If true, water, the lifeblood of Egypt, may also have been the tool that lifted its stones. Imagine this. A block is loaded onto a buoyant raft or barge, then guided into a narrow vertical shaft filled with water. By controlling the water level between different chambers, the block could be floated up step by step. Advocates argue that this would have greatly reduced friction and the need for vast labor forces dragging stones over ramps. Some even suggest that certain internal passages of the Great Pyramid align suspiciously well with what could have been vertical shafts used for such a hydraulic system. Supporters often point to ancient Egyptian expertise with waterworks. The civilization mastered irrigation canals, dams, and basin systems to control the Nile's floods. Large-scale hydraulic engineering was within their capacity, and applying it to pyramid construction would not have been entirely alien to their worldview. In this vision, the pyramid was not just a static monument. It was part of a dynamic, water-based machine built to channel both physical stones and cosmic symbolism. Skeptics, however, argue that no physical evidence of such a hydraulic system has been found inside the pyramid, and the geological structure of the plateau would have posed challenges to sustaining watertight shafts. Moreover, the logistics of maintaining such a system at great heights remain unclear. Still, the elegance of the idea, using the Nile itself as a lifting mechanism, keeps this theory alive among alternative historians and engineers alike. The concrete or geopolymer theory. What if the ancient Egyptians didn't move all the stones at all, but poured some of them in place? This is the radical suggestion behind the geopolymer, or concrete theory, most notably advanced by materials scientist Joseph David Ovitz. He argues that many of the limestone blocks were actually a kind of early concrete, formed by mixing water, limestone rubble, clay, and natron, a naturally occurring soda, into a slurry that was then cast into wooden molds right on the pyramid itself. Once set, the resulting blocks would be virtually indistinguishable from natural stone, but far easier to handle during construction. Evidence cited for this theory includes microscopic analyses of some blocks, which seem to show amorphous structures unlike naturally formed limestone, as well as occasional air bubbles and shell inclusions that look suspiciously man-made. If true, this technique would have been revolutionary, reducing the need to quarry, transport, and lift massive stones, while still producing a monument that appears to be built entirely from carved blocks. It would also explain how some of the highest layers of the pyramid were constructed without requiring impossibly long ramps or cranes. The geopolymer theory fits neatly into Egypt's known expertise with materials. They were adept chemists, using natron for mummification, creating faience glazes, and producing plaster and mortar. Extending this knowledge into large-scale stone casting isn't a huge leap. David Ovitz even conducted experiments to show that such blocks can be made with simple tools and ingredients available in ancient Egypt. Mainstream Egyptologists remain unconvinced, noting that quarry marks, unfinished stones, and tool traces at Giza indicate widespread traditional quarrying and shaping methods. Additionally, not all blocks show signs of casting, and the logistics of casting millions of tons of limestone on-site raise their own challenges. Yet this theory stands out as one of the few alternatives that doesn't rely on lost civilizations or extraterrestrials. Just a clever chemical shortcut hidden in plain sight. Internal casting hypothesis. Stones poured, not carved. Closely related to the geopolymer theory is the internal casting hypothesis, which goes a step further. Rather than casting blocks in molds on the ground and lifting them up, this idea proposes that blocks were poured directly in place inside wooden casings built on each new level of the pyramid. Workers would climb the structure, set up molds on the edges, pour in the limestone slurry, let it set, then move upward. In effect, the pyramid was built like a giant layer cake, each layer being cast in situ. This approach would bypass many logistical nightmares. There would be no need for complex ramps or water shafts to move stones upward. The material itself would travel up in baskets or containers, mixed on site, and then shaped by the molds. It could also account for the extremely tight joints between blocks, as poured stone would naturally settle against its neighbors without gaps. Advocates suggest that this technique might explain why some blocks seem to fit together more like poured elements than carved pieces. Proponents draw parallels with later Roman concrete engineering, which used similar techniques for massive constructions. If Egypt had stumbled upon an early version of this process, it would radically rewrite our understanding of their technological capabilities. Some even argue that the casting molds might have decomposed over time, leaving no trace but the stones themselves. However, critics emphasize that this theory, while elegant, remains speculative. Most geological studies classify the blocks as natural limestone, and there's no direct archaeological evidence of extensive mold infrastructure on the pyramid. Still, as a thought experiment, it offers a powerful alternative to the brute force hauling narrative, one that relies on chemistry, not manpower. Ancient machinery theories. Among the most provocative ideas are those that suggest the ancient Egyptians, possessed some form of mechanical machinery unknown to mainstream history. This doesn't necessarily mean industrial steam engines or modern technology, but potentially advanced cranes, counterweight elevators, or even rudimentary gears and levers beyond what is typically acknowledged. Some fringe researchers propose wooden cranes or hoists that could have been mounted on the pyramid's edges, using counterweights and pulleys to raise stones efficiently. Others imagine large treadwheel cranes, similar to those later used in medieval cathedrals, but made from wood and rope. With enough manpower walking inside these wheels, stones could theoretically be lifted vertically in stages. A few even speculate about lost Bronze Age engines or power sources, though these claims veer deep into speculative territory. One intriguing piece of evidence often cited is the precision of the Great Pyramid's internal passages, some of which are so straight and finely finished that they seem difficult to produce without mechanical aids. Alternative theorists suggest that specialized lifting frames, balance beams, or concealed scaffolding systems may have been used, and that traces of these could have been dismantled after construction. Mainstream scholars caution against underestimating human labor and ingenuity, noting that even without complex machines, simple tools, levers, and coordinated work can achieve remarkable feats. But the allure of ancient machinery persists because it offers a bridge between the purely manual and the fantastical, a middle ground where human intelligence, not extraterrestrials, drives the marvel. Atlantis and pre-dynastic civilizations. Few ideas have gripped the public imagination as fiercely as the notion that the pyramids of Giza are the inheritance of Atlantis, a remnant of a lost civilization that flourished before recorded history. This theory originates largely from Plato's dialogues Timaeus and Critias, where he describes a technologically advanced island empire called Atlantis that sank beneath the waves around 9,000 years before his own time. Over the centuries, various theorists have suggested that survivors of this cataclysm fled to Egypt, bringing with them their sophisticated knowledge, including architectural and astronomical expertise. Proponents argue that the sudden emergence of Egyptian civilization around 3100 BCE seems suspiciously abrupt, as if it were kick-started by an outside influence. They point to the early dynastic period's impressive leaps in engineering, art, and administration, claiming these developments align more with the idea of cultural inheritance than slow indigenous evolution. Some even suggest that the layout of the Giza Plateau and the mathematical constants embedded in the Great Pyramid reflect Atlantean scientific knowledge, a kind of message in stone passed down through generations. The pre-dynastic civilization angle expands this narrative further. It proposes that before the unification of Upper and Lower Egypt, there may have been an advanced culture in North Africa, not extraterrestrial, but human, whose achievements were later absorbed and mythologized by the Egyptians. Advocates point to enigmatic structures like the Assyrian at Abydos, which appears megalithic and older than the temples built around it, as possible evidence of this forgotten era. Skeptics counter that the leap from early Neolithic settlements to dynastic Egypt is well supported by archaeological findings, showing gradual development rather than sudden intrusion. The Atlantean theory lacks physical proof. No Atlantean artifacts have been unearthed, and Plato's story was likely allegorical, yet the allure persists because it offers a romantic, almost mythic explanation. A lost golden age, whose secrets lie buried beneath the sands and seas. Biblical and religious explanations. Long before modern archaeology, people tried to explain the pyramids using the most familiar framework they had: religion and scripture. In medieval and early modern times, travelers from Europe and the Middle East often interpreted the pyramids through the lens of the Bible. 1. Enduring belief held that the pyramids were built by Noah or his descendants as granaries to store food during the Great Flood. This idea stemmed from a mistranslation in the writings of early church fathers, which referred to the pyramids of Joseph. Another interpretation suggested that the pyramids were constructed by the Israelites during their period of enslavement in Egypt. A belief popularized through religious storytelling rather than historical evidence. In these narratives, the pyramids became monuments of suffering, physical proof of biblical events. Though modern Egyptology dates the Great Pyramid to around 2560 BCE, and long before the traditional biblical timeline of Moses, such explanations persisted for centuries and deeply influenced how Western audiences viewed ancient Egypt. Religious frameworks also appear in Islamic traditions. Some medieval Arab historians propose that the pyramids were built by antediluvian kings, rulers who lived before the flood, to preserve wisdom, sciences, and treasures from being lost to the deluge. This echoes the Atlantean narrative in a theological form. The pyramids as repositories of forgotten knowledge from a vanished age. While these religious explanations lack archaeological basis, they're historically significant. For centuries, they shaped how people understood the pyramids, long before modern science emerged. They reveal a deep human tendency to fit the unknown into familiar cosmologies, turning enigmatic monuments into chapters of sacred history. Alien intervention hypothesis. Arguably the most famous and controversial alternative theory is the alien intervention hypothesis. Popularized by Erich von Däniken's 1968 bestseller Chariots of the Gods, this theory proposes that the pyramids were either built or inspired by extraterrestrial beings who visited Earth in antiquity. Advocates point to the sheer scale, precision, astronomical alignments of the Great Pyramid as evidence that primitive humans could not have accomplished such feats alone. Instead, they suggest alien visitors provided advanced knowledge or even machinery to aid construction. The alignment of the Great Pyramid with true north, off by less than a 20th of a degree, is often cited as proof of advanced surveying techniques. The placement of the pyramids in relation to the stars of Orion's belt, the exactness of the base measurements, and the mathematical relationships embedded in its structure are presented as signs of non-human intelligence. In this narrative, the pyramid becomes not just a tomb, but a beacon, a landing site, or a data archive created for cosmic purposes. This theory thrives on unanswered questions and anomalies. How were 2.3 million blocks lifted into place with such accuracy? How did Bronze Age workers manage such vast logistics? If aliens intervened, proponents argue, these mysteries evaporate. Everything becomes a matter of superior technology bestowed upon early humanity. Mainstream scholars firmly reject this hypothesis. Archaeological evidence shows clear stages of construction, quarrying sites, tools, and labor organization consistent with human ingenuity. Yet the alien theory endures in pop culture because it externalizes human achievement, turning the pyramids into proof of cosmic contact rather than terrestrial triumph. It's a story that blends science fiction, mythology, and awe into one provocative package. Atlantean versus extraterrestrial narratives. Within alternative history circles, a curious tension exists between two camps, those who credit Atlantis and those who credit aliens. While both theories reject mainstream explanations, they diverge in their portrayal of the hidden hand behind the pyramids. Atlantean theorists envision a lost human civilization, technologically advanced but earthly in origin. Alien theorists, on the other hand, imagine a celestial intervention that reshaped human history. Some hybrid theories merge the two. They suggest that Atlanteans were either in contact with extraterrestrials or were themselves the descendants of alien colonists. In this framework, the pyramids become the product of a partnership between advanced humans and otherworldly beings, a cosmic alliance encoded in stone. Certain fringe authors go even further, linking the pyramids to global megalithic structures, arguing for a single prehistoric world civilization guided by alien mentors. The Atlantean versus alien debate isn't just academic, it reflects different ways people make sense of mystery. Atlantis emphasizes lost human potential, evoking nostalgia for a forgotten golden age. Alien theories highlight external salvation or manipulation, casting humans as students or pawns of higher beings. Neither theory has concrete archaeological support, but both tap into powerful psychological currents, the desire for grand narratives that explain humanity's greatest mysteries, and the comfort of believing that such wonders could not have been achieved by mere mortals alone. Pyramid energy theories and pseudoscience. In the 20th century, a new set of ideas emerged, less about who built the pyramids and more about what they do. Pyramid energy theories claim that the shape of the pyramid itself channels mysterious forces, acting as a kind of cosmic antenna. This idea exploded in popularity in the 1970s, when experimenters claimed that small pyramids could sharpen razor blades, preserve food, or induce meditative states by concentrating energy. Some fringe researchers went as far as to suggest that the Great Pyramid was an ancient power plant transmitting wireless energy across Egypt. Proponents argue that the pyramid's geometry, especially its golden ratio proportions and alignment with the cardinal directions, allows it to harness subtle electromagnetic fields or even earth energies. According to these theories, ancient Egyptians understood a now-forgotten science of resonance and vibration, using the pyramid as a tool for healing, communication, or planetary stabilization. Critics, including physicists and archaeologists, classify these claims as pseudoscience. Controlled experiments have found no evidence of special pyramid energy, and the supposed razor blade sharpening effect was traced back to mundane factors like air circulation and dehydration. The power plant hypothesis, championed by Christopher Dunn, suggests internal chambers were part of an energy generation system, but this interpretation is speculative and lacks physical corroboration. Nevertheless, pyramid energy theories remain culturally potent. They've inspired New Age movements, meditation practices, and countless popular books and documentaries. In a way, they represent a modern form of myth-making, not about gods or aliens, but about hidden natural forces waiting to be rediscovered. Modern archaeological excavations and discoveries. In the late 20th and early 21st centuries, Egyptology entered what many call its forensic age. Excavations shifted from treasure hunting and tomb raiding to careful, data-driven digs. Archaeologists began to treat the Giza Plateau like a living, breathing construction site frozen in time. One of the most remarkable discoveries came from the area south of the Great Pyramid, a vast workers' village complete with bakeries, breweries, and administrative buildings. Rather than slaves, these were skilled laborers organized into teams, fed with nutritious rations, and housed in surprisingly well-built dormitories. These finds shattered the old Hollywood narrative of chains and whips, replacing it with one of massive state-sponsored labor forces that operated like well-oiled machines. Every pottery shard, bread mold, and animal bone excavated told a story not of oppression but of meticulous planning and logistics. The discovery of ancient harbor installations at Wadi al-Jarf on the Red Sea further deepened this narrative. There, archaeologists uncovered papyri that detailed the transportation of limestone blocks from Tura to Giza, an ancient shipping manifest belonging to an official named Mirror. This was the first-person account ever found of pyramid construction logistics. It described how boats ferried stones up the Nile, and how these stones were unloaded at harbors near the Giza Plateau. This wasn't a mysterious lost civilization. It was organized human ingenuity at its peak. Such discoveries have provided the clearest evidence yet that the Egyptians didn't need alien help or magical technologies. They had a massive, state-managed system centuries ahead of its time. Beyond Giza itself, excavations at lesser-known pyramid sites like Medem and Dahshur revealed transitional phases in construction techniques. For example, the bent pyramid's change in angle halfway up shows builders experimenting with structural stability. These sites are like laboratories, each revealing a step in Egypt's learning curve toward the perfect geometric precision of Khufu's Great Pyramid. Ground-penetrating radar and careful stratigraphic analysis now allow archaeologists to read these sites like layers of a book, uncovering mistakes, adaptations, and refinements in real time. Modern excavations also focus heavily on what isn't visible, such as the buried ramps, storage pits, and foundation trenches hidden beneath the sand. Non-invasive methods allow teams to locate these features without disturbing fragile contexts, leading to a wave of new discoveries even in areas thought to be exhausted. Every season brings fresh revelations, proving that the Giza Plateau still holds secrets waiting patiently for the right tools to unlock them. Laser scanning and 3D mapping of pyramids. The introduction of laser scanning technology revolutionized the way we study pyramids. Unlike traditional measurements, which rely on painstaking manual techniques, laser scanners can capture millions of data points per second, creating ultra-precise 3D models of entire monuments. When researchers applied this technology to the Great Pyramid, they discovered subtle asymmetries in construction details invisible to the naked eye. For instance, the base of Khufu's pyramid is not a perfect square, but shows minute deviations that reveal how builders adjusted to the natural terrain. Even more fascinating is how these scans expose faint tool marks, joints between blocks, and the overall geometry with millimeter accuracy. offering unprecedented insight into ancient craftsmanship. One of the most striking outcomes of this mapping was the discovery of previously undocumented cavities and structural anomalies. Some of these turned out to be simple gaps or erosion pockets, but others hinted at larger intentionally designed spaces. When combined with historical data, these anomalies have led researchers to reevaluate long-held assumptions about the internal architecture of the pyramids. Digital elevation models also reveal how the entire plateau was leveled with incredible precision. In some places within just a few centimeters across vast distances, centuries before laser levels or theodolites were invented. These 3D models are more than academic curiosities. They allow engineers to run structural simulations, archaeologists to plan future excavations without damage, and even the public to experience virtual reality tours that bring ancient Egypt to life. In some cases, scanning has even revealed areas of past restoration done by earlier Egyptologists, helping modern teams distinguish ancient structures from modern interventions. This fusion of ancient stone and modern light technology is creating a digital backup of the pyramids that will outlast even the monuments themselves. Perhaps the most profound result of laser scanning is the ability to compare multiple pyramids across dynasties with mathematical precision. By overlaying scans of Medum, the Bent Pyramid, the Red Pyramid, and Khufu's masterpiece, researchers can visualize centuries of architectural evolution, like time-lapse photography. It is as if the stones themselves are telling their story, one precise beam of light at a time. Muna tomography, peering inside without excavation. In 2017, the world was stunned when physicists working with the Scam Pyramids project announced the discovery of a large void inside the Great Pyramid using cosmic rays. Muon tomography, a technique originally developed for nuclear research, measures the passage of high-energy particles called muons through solid structures. Because muons are absorbed differently by empty space versus stone, scientists can create X-rays of massive monuments without drilling a single hole. The resulting images revealed a mysterious cavity above the Grand Gallery, a space at least 30 meters long, never before documented. Unlike traditional archaeological methods, Muon tomography is passive, relying on naturally occurring cosmic rays. Detectors placed inside and around the pyramid recorded particle trajectories for months, gradually building a three-dimensional density map. What emerged challenged the assumption that the Great Pyramid's internal layout was fully understood. While Egyptologists debate whether this void is a hidden chamber, a relieving structure, or a construction gap, the discovery has undeniably shown that the pyramid still holds uncharted spaces within its core. Muon scanning also offers unprecedented accuracy in confirming the positions of known chambers. For example, it reaffirmed the exact shape and orientation of the king's chamber and its relieving chambers without any invasive techniques. This is particularly important because traditional excavation inside the pyramid is strictly limited for conservation reasons. By using muons, researchers can effectively see through millions of tons of limestone, a feat no other technology currently matches. The implications of this technique extend far beyond Giza. Muon detectors are now being deployed at other sites, including the Bent Pyramid and even Mayan temples, opening a new era in global archaeology. For the first time, humanity has the tools to map the hidden architecture of ancient monuments with the same clarity that we map the human body with medical imaging, material science, analyzing stone composition. While construction theories often focus on ramps and labor, the stones themselves hold critical clues. Material scientists have been analyzing the composition of pyramid blocks using techniques like X-ray diffraction, petrographic microscopy, and electron microprobe analysis. These studies reveal not just what the blocks are made of, but how they were sourced, transported, and weathered over time. The fine Tura limestone casing stones, for example, contain tiny fossilized shells and show signs of precise quarrying, indicating they were carefully selected for both strength and beauty. Granite used in the king's chamber, sourced from Aswan nearly 800 kilometers away, has been studied to determine tool marks and transportation methods. The surfaces show traces of pounding with dolerite balls, combined with copper tools that left microscopic grooves. These marks allow researchers to reconstruct the sequence of cutting, shaping, and finishing, like forensic detectives solving a 4,500-year-old engineering puzzle. Moreover, Isotopic analysis of water trapped in some limestone suggests quarrying occurred during specific Nile flood seasons, aligning with labor cycles. One of the most fascinating debates in material science surrounds the geopolymer hypothesis, the idea that some blocks were cast rather than carved. While mainstream scholars largely attribute the blocks to traditional quarrying, some microstructural studies do reveal unusual binding phases that could indicate limited use of reconstituted limestone. Whether or not this was widespread, such findings show that ancient Egyptians may have experimented with more than one technique depending on the location and purpose of the stones. Modern conservation efforts also rely heavily on material science. By understanding the composition and degradation patterns of ancient stones, engineers can design appropriate restoration materials that don't accelerate decay. In a sense, these analyses bridge the gap between the builders of the past and the conservators of the future, all through the language of minerals and molecules. Experimental archaeology, rebuilding pyramids today. If theory and speculation dominate much of pyramid construction discourse, experimental archaeology cuts through it with sweat, tools, and stone. Since the 1970s, various teams of engineers and Egyptologists have attempted to replicate ancient building techniques on a smaller scale to see what actually works. One of the earliest serious experiments was led by Mark Lenner and Roger Hopkins in the 1990s, who built a 6-meter-high mini-pyramid using copper chisels, wooden sledges, and ropes. Their team discovered that cutting limestone with copper tools is possible, though time-consuming, and that wetting the sand dramatically reduced friction when hauling sledges, confirming a detail found in ancient tomb reliefs. Perhaps the most famous modern experiment came in 2002, when a Japanese team attempted to build and move a 2-ton block with the methods proposed by mainstream Egyptology. Their first attempts failed spectacularly. The sledges broke, ropes snapped, and the block sank into the sand. But after adjusting the sledge design and wetting the sand, the team found they could move the block with about 20 people, achieving a surprisingly efficient system. These experiments showed that much of the impossible labor narrative comes from underestimating ancient engineering knowledge and overestimating the difficulty of moving large stones with coordinated human power. More ambitious projects have tried to scale up. In the late 1990s, French architect Jean-Pierre Houdin proposed his internal spiral ramp theory and worked with teams to model and test ramp gradients. Others have attempted to carve and transport granite using dolerite pounders and simple wooden levers, demonstrating that such tools can shape even the hardest stones with patience and skill. These experiments aren't meant to perfectly replicate history, but to establish a range of plausible methods that could explain the ancient achievements without invoking extraordinary technology. Experimental archaeology also reveals the human element often lost in academic papers. Participants report that once teams fall into rhythm, hauling blocks becomes a kind of synchronized dance, with chanting and coordinated pulling creating momentum. This echoes ancient depictions of laborers singing and working in teams. A reminder that the pyramid builders were not faceless masses, but organized, skilled people. Each successful experiment chips away at the myth of impossibility, bringing the methods of 4,500 years ago into modern hands. Engineering simulations and computer modeling. While experimental archaeology tests physical methods, computer simulations allow researchers to push beyond what's practical in real life. It's using finite element analysis, structural modeling software, and physics engines. Engineers have built highly detailed virtual models of the pyramids and potential construction techniques. These simulations reveal how different ramp designs would have behaved under real-world forces. Straight ramps would require massive amounts of material. Spiral ramps introduce lateral stress. And hybrid systems often offer the most efficient compromise. Such modeling helps explain why some ramp theories are more plausible than others from an engineering standpoint. Simulations also allow researchers to reverse engineer the construction sequence. By virtually deconstructing the pyramid, layer by layer, teams can identify where ramps may have intersected, how blocks were positioned, and where internal spaces were left open temporarily. For example, some models suggest that the Grand Gallery may have functioned as a massive internal ramp or counterweight system during construction. A hypothesis supported by its unusual design and lack of clear ceremonial purpose. Computer models bring these possibilities to life. allowing researchers to watch virtual stones slide into place just as ancient builders might have done. Perhaps the most striking contribution of simulations is in stress analysis. Engineers have run models to see how the weight of millions of tons of stone distributes through the pyramid's core. These models confirm that features like the relieving chambers above the king's chamber are not decorative. They are critical structural innovations that prevent catastrophic collapse. Simulations also explain why certain cracks and deformations appear in the internal chambers today. They're not evidence of poor construction, but natural settling after millennia. Beyond construction, computer models are also used to simulate how the pyramids have weathered time. Wind erosion, temperature fluctuations, seismic activity, and ground shifts can all be mapped to understand why certain blocks have survived better than others. This information not only informs restoration, but also provides insight into how ancient Egyptians may have anticipated some of these stresses through careful site selection and foundation work. Acoustic and electromagnetic properties of pyramids. Among the most intriguing areas of modern scientific investigation is the study of the acoustic and electromagnetic properties of the pyramids. 8. When engineers and physicists analyzed the king's chamber, they discovered that its granite walls resonate at specific frequencies, creating a kind of natural echo chamber. The chamber's dimensions appear to amplify certain sound waves, particularly low-frequency tones. Whether intentional or coincidental, these resonant properties would have produced a powerful auditory effect for anyone chanting or speaking within the chamber, possibly enhancing religious rituals or ceremonies. Acoustic studies have extended to the Grand Gallery and other interior spaces, where unusual sound propagation patterns have been detected. Solar alignments and astronomical precision. Perhaps the most jaw-dropping aspect of pyramid engineering is its astronomical alignment. The Great Pyramid's sides are oriented to the cardinal directions with an error of less than 1/15 of a degree. It's a level of precision that rivals modern surveying equipment. Recent studies suggest that builders used the circumpolar stars as reference points, tracking their movements to determine true north with incredible accuracy. Some Egyptologists believe they may have used a simple gnomon vertical pole and observed star transits, while others propose sighting instruments aligned with specific constellations like Ursa Major and Ursa Minor. Beyond cardinal orientation, the layout of the Giza Plateau seems to reflect deliberate cosmic planning. The three main pyramids are arranged in a pattern some have likened to the belt stars of Orion. While the so-called Orion correlation theory is controversial, there's no doubt that the ancient Egyptians placed immense importance on stellar alignments. The shafts in the king's chamber and queen's chamber, once thought to be ventilation ducts, align with stars like Sirius and Orion's belt stars associated with rebirth and the afterlife. These alignments may have served as symbolic stairways for the pharaoh's soul to ascend to the heavens. Solar alignments are equally striking. The descending passage of the Great Pyramid aligns with the star Thuban, the ancient pole star, while other passages are oriented toward the rising and setting sun on specific dates. The precision of these alignments implies long-term astronomical observations and an understanding of the sky far beyond simple observation. This celestial knowledge was deeply embedded in Egyptian religion, where the pharaoh's journey after death mirrored the sun's daily voyage across the sky and the stars' eternal cycles. Modern astronomical software has allowed researchers to rewind the night sky thousands of years, confirming that these alignments matched celestial configurations at the time of construction. This ability to time travel through astronomy reveals that pyramid builders worked with both the earthly and the cosmic, their monuments rooted in the bedrock of the Nile Valley, but aimed squarely at the stars. These were not random piles of stone. They were cosmological machines, aligning human ambition with the eternal rhythms of the heavens. Pyramids in the Roman and medieval imagination. When Roman explorers first laid eyes on the pyramids, they were already over 2,000 years old, monuments from a civilization as ancient to them as Rome is to us today. Roman writers like Pliny the Elder and Strabo recorded their impressions with awe and speculation. Pliny, for example, wrote that the pyramids were built for no useful purpose, but merely to show the wealth and power of kings. Others suspected they hid unimaginable treasures or secret chambers, though none during the Roman period managed to uncover anything substantial. The pyramids were both tourist attractions and objects of mystery for wealthy Roman travelers. who often visited Giza as part of a kind of early grand tour. By the Middle Ages, as direct contact with pharaonic culture faded, the pyramids were reinterpreted through the lens of biblical and Islamic traditions. Medieval Arab historians such as al-Makrizi and al-Idrisi proposed that the pyramids were built by antediluvian kings-rulers before the Great Flood to store knowledge, treasure, and magical artifacts that would survive catastrophe. Some texts even suggested that Hermes Trismegistus, a legendary fusion of the Egyptian god Thoth and the Greek Hermes, instructed humans to build the pyramids to safeguard sacred wisdom. These tales transformed the pyramids from royal tombs into vast repositories of secret knowledge, a theme that would echo through centuries of esoteric thought. Medieval visitors often left inscriptions on the stones, including verses from the Quran, poems, or names of explorers. Many believed the pyramids were the granaries of Joseph described in the Book of Genesis, interpreting their massive shape and durability as evidence of their function during the biblical famine. This blend of scriptural interpretation, folk legend, and genuine curiosity created a rich tapestry of medieval pyramid lore shaped European perceptions for centuries to come. Even without scientific understanding, the Roman and medieval fascination with the pyramids demonstrates a universal human impulse to project meaning onto ancient structures. These monuments became mirrors reflecting the cultural values of each era, whether imperial grandeur, biblical prophecy, or mystical wisdom. 18th century Egyptology and the birth of pyramidомania. The 19th century was a turning point. Napoleon's 1798 campaign in Egypt brought not only soldiers, but also scientists, artists, and scholars, the savants, who meticulously documented Egypt's monuments in the monumental description, De l'Egypte. Their work ignited an Egyptomania that swept across Europe. The Great Pyramid became a subject of intense measurement and mapping. Surveyors like Sir Flinders Petrie brought a new scientific rigor, measuring angles, stone fits, and internal chambers with astonishing precision. Petrie's work laid the foundations of modern Egyptology and shattered many medieval myths with hard data. But alongside this sober science grew a feverish cultural fascination, what historians call pyramidомania. Adventurers tunneled into the pyramids seeking treasures. Some dynamited their way in, leaving scars still visible today. Wealthy tourists carved their names into the limestone, while authors published sensational accounts of secret chambers and ancient wisdom. Freemasons, theosophists, and mystics saw the pyramids as cosmic archives, linking them to Atlantis, the lost tribes of Israel, or mystical initiation rites. In Victorian London, lecture halls were packed with audiences eager to hear theories about the pyramids, prophetic measurements that supposedly predicted future events. The 19th century also saw a dramatic rise in mummy unwrapping parties and the display of Egyptian artifacts in European museums acts that both popularized and distorted ancient Egypt. The pyramids, towering over this frenzy, became both scientific laboratories and blank canvases for Western imagination. For some, they were monuments to human ingenuity. For others, proof of lost civilizations or divine intervention. This tension between archaeology and mysticism has never fully disappeared. By the late 1800s, the Great Pyramid was no longer a distant curiosity. It was a global icon. Telegraph lines, steamboats, and later photography connected Giza to the wider world, turning it into both a site of rigorous study and mass spectacle. The modern myth of the pyramidas, both rational marvel and mystical enigma, was born. Pyramids and occult and esoteric movements, though ancient structure has been absorbed into modern esotericism quite like the pyramid. In the late 19th and early 20th centuries, secret societies and mystical orders adopted pyramid symbolism as a central motif. The Hermetic Order of the Golden Dawn, for example, viewed the pyramids as repositories of ancient magical knowledge. Freemasonry, too, integrated pyramid imagery into its symbolism, seeing in the Great Pyramid a kind of universal temple that encoded divine geometry and cosmic truths. The idea of the pyramid as a mystical machine gained traction through works like Charles Piazzi Smythe's Our Inheritance in the Great Pyramid 1864. Smythe believed that the pyramid's measurements encoded biblical prophecy and universal units of measurement, so-called pyramid inch, though his theories were later debunked. They inspired generations of occultists who saw the pyramid as a tool for spiritual awakening or as proof of an advanced lost wisdom. In the 20th century, the New Age movement gave the pyramid a new role, a spiritual energy generator. Pyramid-shaped meditation chambers became popular, with adherents claiming that the geometry focused cosmic energy, enhancing healing and consciousness. Some believe that placing food or razors under small model pyramids preserved them longer, an idea called pyramid power that surged in the 1970s. While scientifically unfounded, these beliefs showed how the pyramid's aura had expanded from historical monument to spiritual technology. Occult and esoteric interpretations often reveal more about modern cultural desires than ancient intentions. They speak to a yearning for hidden knowledge, a belief that somewhere within those limestone blocks lies a secret that could unlock human potential. The pyramid became not just a symbol of death and kingship, but of cosmic mystery and personal transformation. Pop culture, movies, and conspiracy theories. If 19th century pyramidomania was fueled by explorers and mystics, the 20th and 21st centuries have been powered by film, television, and the internet. Hollywood turned the pyramids into icons of adventure and mystery, most famously in films like The Mummy, 1932, 1999, Stargate, 1994, and countless others where they serve as portals, alien landing sites, or cursed tombs. These cinematic depictions have often blurred fact and fiction, but they've also kept the pyramids at the center of global popular imagination. Television has had an even greater impact. Series like Ancient Aliens turned the pyramids into linchpins of extraterrestrial conspiracy theories, suggesting that their precision and scale could not have been achieved by humans alone. These claims, though widely debunked, have attracted millions of viewers and created entire online communities devoted to alternative explanations. YouTube channels, blogs, and forums buzz with debates about hidden chambers, electromagnetic energy beams, and alien architects, often mixing kernels of real archaeological data with vast layers of speculation. Pop culture has also transformed the pyramids into instantly recognizable branding tools. From album covers and corporate logos to fashion and video games like Assassin's Creed Origins, the pyramid is shorthand for mystery, endurance, and the unknown. Even memes and TikToks play with pyramid conspiracies, turning ancient architecture into digital folklore. This blending of entertainment and pseudo-history can be frustrating for scholars. But it also demonstrates the pyramid's unparalleled cultural magnetism. Few monuments have managed to infiltrate every medium from sacred texts to sci-fi blockbusters quite like these Egyptian giants. Tourism, preservation, and modern Egypt. Today, the pyramids are at once global icons and fragile archaeological sites. Millions of tourists flock to Giza each year, drawn by the promise of standing before one of humanity's oldest wonders. This influx fuels Egypt's tourism economy, but also places immense strain on the monuments. Foot traffic erodes stone floors, pollution from nearby Cairo darkens the limestone, and unauthorized climbing has occasionally caused damage. Preservation has become a balancing act between sharing the pyramids with the world and protecting them for future generations. Modern preservation efforts involve both traditional restoration techniques and cutting-edge technology. Laser cleaning, 3D mapping, and controlled visitor pathways help mitigate wear and tear. Egyptian authorities, often in partnership with international teams, have invested in stabilizing structures, restoring casing stones, and monitoring microclimates inside the chambers to prevent further degradation. The pyramids, once built to last forever, now require vigilant human stewardship to survive the modern world. Tourism has also reshaped the cultural landscape around Giza. The plateau is no longer isolated desert, but an urban-adjacent site with hotels, restaurants, and even sound and light shows projected onto the stones at night. While some criticize this commercialization, others argue it keeps the pyramids alive as active cultural landmarks rather than static ruins. For Egyptians, the pyramids are not just relics. They are living symbols of national identity, pride, and resilience. Preservation challenges remain significant, but so does the global fascination. Even in an age of digital replicas and virtual tours, nothing compares to the experience of standing at the foot of the Great Pyramid, looking up at its massive form and feeling history pressed down like the desert sun.
Our future.
For over 4,500 years, the pyramids have stood as silent witnesses to the rise and fall of civilizations. Yet paradoxically, the most exciting discoveries may still lie ahead. The future of pyramid research is moving beyond excavation and traditional archaeology. Instead, it's entering a new frontier of non-invasive technologies, interdisciplinary collaboration, and global research initiatives. One of the most promising tools is Moine tomography, a cutting-edge scanning method that uses cosmic rays to detect voids within solid structures. In recent years, teams using this technology have discovered mysterious hidden chambers within the Great Pyramid that were previously unknown. Despite centuries of exploration, these voids have ignited intense debates among Egyptologists and engineers alike. Are they simple construction gaps? Or could they be undiscovered ceremonial spaces, relieving chambers, or even hidden passageways? The fact that such questions remain unanswered today shows how much of the pyramid's interior remains unexplored. Equally important is higher-resolution 3D mapping, which is providing unprecedented detail about both the interior and exterior of these structures. Modern drones and laser scanners allow researchers to digitally reconstruct entire pyramids, stone by stone, with millimeter precision. This data doesn't just aid conservation, it allows engineers to run advanced structural simulations that can reveal how these buildings respond to forces like gravity, earthquakes, or even centuries of erosion. By feeding this information into AI models, researchers can generate hypothetical construction sequences, testing ancient ramp theories, or identifying anomalies that suggest previously unknown construction methods. Beyond technology, the future of pyramid research is increasingly collaborative and inclusive. Egyptian archaeologists now lead many major projects, supported by international teams that bring in specialized expertise in fields like material science, geophysics, and computational modeling. Ethical considerations are also evolving, rather than breaking new tunnels into the pyramids. Future research emphasizes preservation-first exploration, using sensors and digital twins to enter the monuments without causing harm. And then there's the wild card: unexpected discoveries. History has repeatedly shown that Egypt still holds surprises, whether it's the rediscovery of lost tombs, the uncovering of ancient workers' villages near Giza, or sudden revelations from beneath the desert sands. As technology advances and research accelerates, it's entirely possible that the next generation will rewrite chapters of pyramid history that we